back, we're live. We're ThinkTech. Wow, we're excited to be here. Shiv Sharma is with us. He's excited to be here too, am I right?
Yes.
This is what, his third appearance on ThinkTech, yeah?
Yes.
That's great. Now, Shiv Sharma is a PhD researcher at UH. He's the Associate Director of the Hawaii Institute of Geophysics and Planetology, and it's HIGP. And that is in the School of Ocean and Earth Science and Technology, SOWEST at UH. And it is a great school. It's a great institute and a great school. And he is a world-class global researcher doing things that extend to Mars.
Thank you.
We're going to find out about them today. But before that, I want everybody to know your training, credentials, and how you got to be what you are today so that they can get your job.
Okay, sounds good.
Tell that camera, tell camera 2 over there.
Yeah, so I got my PhD in physics from Indian Institute of Technology.
That's a very, very good school, top school in India.
Yeah, and
IIT, yeah.
Yeah, so then I went to, I was interested in high pressure, and there was the opportunity at the University of Leicester in England. So I went there, and I was working on squeezing minerals and chemicals under high pressure. And one day I came across an article the Russians made hydrogen metallic. And so it caught my eye, and they were just measuring resistivity. So I thought if I put it in the diamond cell and measure on my spectrum, I can do that. At the same time, there was a paper in Science from the Geophysical Laboratory in Washington, D.C., and they could go to the high pressure, like 1.7 million atmosphere. So I wrote to them, I said, I would like to come and work. So I went to Washington, D.C., and that was my introduction to earth sciences. And so there I worked on melts, silicate melts, which are the part of the lava in the volcano, and also worked on hydrogen. And I could freeze hydrogen at 57,000 atmosphere. Hydrogen?
Hydrogen, okay.
Hydrogen gas.
Yeah, and you can compress it.
You compress it at room temperature, and it goes solid. And so.
Really? Didn't know that.
Yeah. So I worked on that, and then I gave to lecture at the American Geophysical Union meetings, and some people from Hawaii, they wanted me to come here and give a talk. And so I visited them, and the director asked me if you'd like to stay here. This was December. I had all this heavy coat from the East Coast. The place looks like heaven. So I said, yeah, sure.
Yeah.
I guess I moved to Hawaii in 1980.
Yeah.
And so.
It's 35 years ago, actually.
Yeah, and so I set up a lab. It's called Raman Spectroscopy Laboratory. And we do micro-Raman, looking at the minerals and meteorites. And that has been growing in time. And then 15 years ago, I got involved in looking at with a telescope to look at the minerals at a distance. And while I was here, there's a geothermal well, and so they want to measure the temperature inside the well. So in collaboration with the Livermore National Laboratory, we had an optical fiber, we lowered it, and we measured the temperature on Big Island. That was fun. And so I've been doing multidisciplinary research.
Yeah, but it's all around identifying
Materials. Yeah.
And I guess when I say materials, I may not know all the materials you're looking to identify, but that means materials on the periodic table of elements. Am I right?
Yeah, we can do elements too, but mostly I was doing was the molecules in the solids. So
that's even more complex, isn't it? Because molecules are more complex.
So what happens is molecules give a vibrations, and they are very characteristic. So if you can look at the vibrations on the molecules, you can identify it. They're basically like fingerprints. So you can see this is this molecule, this is other molecule. So then I got involved with the medical school people and looking at the cancer cells and looking at even on the E. coli.
We're going to break this down by all the projects, but the general notion of it is you're the CIS guy. You can identify molecules in space.
Yeah.
In a micro
Raman, microscopic samples.
I mean, it's
also
whatever they are, you can identify them.
Yeah, and when working on this Mars project, we also can identify elements in the rocks. what called a laser-induced breakdown spectroscopy. So it's all spectroscopy, but it just sublimes very small amount of material, produce a plasma, and you can look at the atomic emission lines.
Okay, so I want to go through these one by one.
Sure, yeah.
Just, so spectroscopy, which you just talked about, that's light.
Yeah,
Okay, so you can shine a light, or you can look at light that's
Yeah.
emanating from an
Yes.
element.
Yes.
And an element is something on the periodic table.
yeah,
And, it just still blows my mind to find that our universe, we already know the elements.
yes.
They're on the table already.
Yes,
And we learned that on Earth.
yes,
So what we find here is that the elements on Earth that's the whole shebang for all of our universe.
yeah,
There's nothing out there that's not on our table already.
that's true.
That's fabulous. Okay, so anyway, if you look at the light coming in from this, you can identify the element, the atom.
Yes, yeah, sure.
The atom. Okay, then if you listen to the vibrations,
Of the molecules.
you can identify the molecule.
Yes,
And then if you, Raman, I remember last time we spoke, I was making jokes about ramen being a food,
yeah.
but it's not a food, is
No,
it?
it's not.
What is it? What is ramen?
Is an Indian scientist in 1928. He discovered when light get inelastically scattered, and that carry the information about the vibration of the molecules. And for that, he was awarded Nobel Prize in 1929, and the effect is known as Raman effect, and then it became known as the Raman spectroscopy.
Which is the vibration?
Yeah, look at the vibration of the molecules,
molecules.
in liquids, solid, gases, and you can identify what kind of molecules are in there.
You can use that in a micro fashion
Yeah,
for just very close in the or you can look at a distance also?
yeah. So for looking at the microscopic scale, we use a microscope, and for looking at a distance, we use a small telescope. And so you can look at at a longer distance. We have detected things at 120 meters away, and we use a pulse laser, and then and the sunlight doesn't matter, so you can measure daytime or nighttime measurements.
So how do you, 120 meters away, how do you determine the vibrations in a molecule?
Yeah, because what happens is when the light interacts with the molecules, it changes its wavelength. So those fingerprints comes out, and you can really detect it. It's like when an audio frequency, they mix with the RF frequency, and we transmit it, and the other end you just separate them out.
It's the same thing, huh?
Yeah, so it's similar effect,
Yeah.
yeah.
So-
But it's at a quantum level, at a very, very, very molecular level, I think, yeah.
So the vibrations have frequencies, they have characteristics.
Mhm.
They leave, because of the frequencies and I guess the wavelength, the waveform
Yeah.
of these vibrations, you can look at that and identify the signature of that
Yes.
molecule.
Yeah. If you measure directly, they lie in the infrared region of the spectra. And so we have got two kind of vibrations. One is the rotational molecules, and they are like in microwave. We cook food with that. And the other one are in the infrared. And then they also can be detected indirectly by interaction with the laser light. And then we can learn about the molecules.
These things are at the cutting edge, aren't they?
Yeah.
I mean, this is now. This did not exist when you came to Hawaii at all.
No, they were
You've been
existing.
following the action very closely, haven't you?
Yeah, they actually were discovered in 1928, as I mentioned. So, but what happened is with the technological advancement,
Yeah.
we got the lasers, which are very strong sources.
Yeah.
And then we also got the electronics, they call it CCD camera, like you have one here.
Yeah.
And you can measure it. In the old days, they used to use a photographic plate, and it used to take a week to measure the spectrum. Now it takes less than a second.
And you've been advancing this technology?
Yeah, sure, yeah.
You've been writing papers about it.
Oh, sure, yeah.
Yeah.
It is actually at HIGP, we have a state-of-the-art laboratory, and so we can do all these things.
That's fabulous.
And I'm collaborating with the Los Alamos National Laboratory people on this Mars 2020 rover mission, so.
We're going to talk about that.
Yeah.
I just, one point before we go to the break. I remember Oceanit, right down the block here, Oceanit, was working with LIDAR in determining wind directions
Yes.
and velocity,
Yeah.
with the idea of helping a windmill developer,
Yeah.
wind turbine developer,
Yeah.
site the wind turbine in the optimal place.
Yeah.
I don't think they finished the project, they ran out of funding or something. But,
Actually, they have been working with me too. I helped them out.
oh, on that project?
No, the other one, like looking at, they have some project on some materials, and then they also had one project on this fish poisoning. What do you call it? So they brought some sample in the lab, and
That's
I helped
nice.
them. Yeah. So
Yeah.
I know those guys.
Yeah, well, that's great.
Yeah.
I mean, these projects are all so interesting, and they all require such innovation and creative thinking, and you
Yeah.
live in a world of that.
Yes.
One thing after another, there's no boundary, except there's this common denominator. You must know what it is.
That's
You are
right.
determined to find out what everything is.
Yes, that's right. Yeah.
We'll take a short break now. We'll come back with Shiv Sharma in a minute. He's a researcher and associate director of the Hawaii Institute of Geophysics and Planetology. We are delighted that he's here, that we can talk to him. We'll be right back.
Aloha, my name is Roy Kodani, and every Wednesday at 1 p.m., I host Life in the Law, which is a segment of ThinkTech Hawaii. And basically, I host guests who have some relevancy to law in Hawaii. And I hope you will continue to tune in. If you have questions, tweet us at ThinkTech Hawaii. Mahalo.
Aloha, I'm Kirsten Baumgart-Turner, and I host Sustainable Hawaii every Tuesday from 11 a.m. to 12 noon. My guests offer insights on challenging economic and environmental issues facing our state and offer innovative solutions to increasing Hawaii's long-term sustainability. Recently, we've been focusing on sustainable land development, food, and energy security. If you have a project or issue you'd like to discuss on the show or would like to be a guest, please contact me at kirstenbturner@gmail.com and tune in live weekly or view the show at your convenience at thinktechhawaii.com. Mahalo.
Based on the looks. Okay, we're back. We're live. Talking with Shiv Sharma, who is at the Hawaii Institute of Geophysics and Planetology. He's the associate director, and Rhett Butler is the director. Am I getting
Yes.
that right? Okay. Hi, Rhett. Shout out to Rhett. Thank you, Rhett. Okay, so anyway, I want to talk about these projects you're working on so we can get a sort of a four-square idea of how you find out what things are. And one of them is the micro ramen. And I guess that means ramen is looking for vibrations, and micro is when you're looking
Very small samples, yeah.
So what are you doing in that lately?
Yeah, so when I came here, I started with looking at the micro Raman system. We looked at the effect of temperature on minerals, which are the part of the volcano, and then also look at the melt structure and how it reacts with gases and things like that. And then we also look at the meteorites samples. And that was also then led to the development of application in material sciences as well as into biomedical sciences. So the micro Raman, you can look at, the cells are very small. And so we developed the techniques for looking at these things and reanalyzing them with the micro Raman system.
Like you're working with Dr.
Kamimoto,
Lori Kanimoto,
Yeah.
who's an MD researcher in OBGYN at the Cancer Research Center of the medical school.
Yeah, so there was an announcement from National Institute of Health for translating research. So you do some research and apply it. So I thought, well, maybe we apply for a grant and all that. So I tried to find out so will be interested, and Laurie was very much interested in it.
You had the idea, though. You approached her. I did want to get that straight.
Yeah.
Now, here's a guy who works on planets a million billion miles away. Well, 50 million anyway. I know that because I watched the movie The Martian, and I know that Mars is 50 million miles away. But now he's going to work on cancer right here at
Close
the
to the
John A.
home.
Burns School of Medicine.
Yeah.
Fabulous.
That's correct, yeah. So she got the Cancer Research Center, and they have frozen samples from cancer patients. And so since she's the OB/GYN, she was interested in looking at cervical cancers and the ovarian cancer, and we analyzed it, and we could identify the difference between the normal cells and the cancerous cells.
This is a big deal in cancer research, isn't
Yeah,
it?
sure, yeah.
To be able to distinguish a good cell from a bad cell.
Yeah.
It's a critical piece of cancer research.
Mm-hmm.
So
Yeah.
you're absolutely certain when you look with your micro-Raman?
Yeah, sure, 100% sure.
Ha!
Yeah,
Now, no, but you have to be able to see it?
yeah.
Can you go down deep and then, next level of cells and all that? Or are we talking about a slide?
No, they were thick slides, and so you can look at individual cells, and so it's published work, and so
In the journal,
applied spectroscopy.
okay.
Yeah.
Spectroscopy.
Yeah, so there was a little problem because the people who do pathology, they use dyes to identify different cells, and when we did initial experiment, we only could see those dyes and the chemicals they treated it. So then we got these fresh frozen samples without any dye, and then we could look at those, because technically it's so sensitive that you can see the other molecules around it. So yeah, so it took a little,
But without any dye,
yeah,
you're just looking at the fresh frozen,
yeah,
and you can see exactly the line of cell, the margins, so
Yeah.
to speak,
Yeah.
of the cancer cells and the ordinary
normal
cells.
cells, yeah.
Isn't that interesting? This is earth-breaking.
Yeah, it
shattering.
is, yeah. There's a lot of work going on at MIT and other places, and it can also define the margin of the cancer.
Yeah.
So when they take out in the surgery, remove it,
Yeah,
sometimes they miss it and then it comes back.
yeah.
And so if you identify it, then you can really remove it, and then.
So if I'm having cancer surgery
Mhm.
and you do a slide to see if you got it all out,
No, so they have done optical fibers.
Yeah.
So they can look at lung cancer, they can just lower the cancer and then can look around.
yeah,
And so you can really do in the operation theater, because it's kind of interesting, because for going to Mars, we developed a Raman spectrometer, which is very small, 6 inches by 4 inches. So you can roll this thing in the operation theater, and you can do it right there. And since it can work during bright lights, which are operation theater lights are bright, and you can make measurements without any problem.
so you do it right there during the
Yeah,
operation.
yeah.
You know if you got the margins
Yeah.
right there in the operation. That's huge. Is it happening now, or you still have to do some work to get it there?
Yeah, it's actually other people are doing it, but it's difficult to work with MD people because not many people are interested in research. They are more interested in looking after the patients.
Yeah, yeah.
And so, but it is a potential to.
Huge
use it.
potential, yeah.
Then I moved to Mars, so.
Yeah. Well, we need to talk about Mars.
Yeah, sure, yeah.
Now, full disclosure,
Mm.
I took my wife to see the movie
Mhm.
this past Saturday night, and we were blown away by this movie.
Oh, I see.
It
yeah.
was great. Now, you saw it too.
Yeah, sure.
How could you not? If you're doing research about Mars, and you're involved in the Mars trip in 2020, how could you not?
Yeah, sure.
You didn't consult on making the movie, did
No,
you?
not really, no.
Okay. And one thing I heard on Hawaii Public Radio was that the movie, except for one point, the movie was scientifically accurate.
Mhm.
The one point that it was a little Hollywood
Oh, yes.
was the dust storm.
Oh, yeah.
And they said the dust storm in Mars would not be that extreme, but they wanted to give you a little drama to open your thinking about Mars.
Oh, yeah.
And certainly.
But our instruments can detect things in the dust storm as well.
Yes, oh, no,
Yeah.
oh, that's right, that's
Yeah.
right. You
Yeah.
can see through the dust.
Yeah,
And you can evaluate what's in the dust.
Yeah.
Using your Raman
yeah, that's
technology.
telescopic Raman system, yeah.
Yeah, yeah. So anyway, the movie was a great movie.
Yeah, sure.
And, just to look at some of the technologies that were going on, I mean, one is they were able to do all these space maneuvers manually. I thought that was pretty interesting. I mean, without all the computers, they could actually do it manually. And I guess that's a valid point. And he was able to grow food. That was the most interesting. The botany aspect of the movie. He was able to grow food in their shelter in Mars.
Oh, yeah.
And thus survive. He was left behind, and he had to survive, and he needed food, and he grew the food himself, and that was a first. But I guess people say that all that could be done. So
Yeah, sure. I think I went to NASA Langley Research Center, and those people are working on how to make shelters and how to grow food there. And so if you get a plant there, they use CO2, which is on Mars,
Yeah.
and then they release oxygen. So if you get a right combination of things, you can convert the planet Mars into Earth-like system.
Yeah, yeah.
So,
Well, it was very interesting to watch. I mean, on movies these days, when they get technical and scientific like this, to me, they become fascinating.
Yes,
I'm
sure.
sure you loved it too. So let's talk about your Mars trip. This is not the first Mars trip. This is the
this will be the next in Mars in 2020.
2020. What
Yeah.
are you doing to facilitate this
So
trip?
there is the instrument and the Curiosity rover, which is right now there. They have one laser instrument. It's called CAM-CAM.
CAM-CAM.
Yeah. So the CAM-CAM has a camera, also have a laser, and it does uses a technique called LIBS. It's a laser-induced breakdown spectroscopy. So you can find out the elements in the rocks, and they have been doing great because they have made thousands of measurements. Every time they put a spark, and you get a composition of the material.
Why do they do that?
Just to find out what kind of rocks are there. The only problem is they cannot find what the minerals are there. So because they have to create the elements and try to put it together. A lot of rocks are glassy. They don't have minerals in there. So this time when we wrote the proposal, we included the Raman and also a technique called laser-induced breakdown spectroscopy and the LIBS.
Okay, what is the laser-induced
Breakdown
breakdown
spectroscopy.
spectroscopy?
Basically, you have a very intense laser pulse, focus it on a small spot, and it vaporizes a small amount of material in nanograms.
Then you look at the vapor, don't you?
You look at it produces a spark, and you look at the spark, and that has a atomic emission lines.
And then you can tell what it is.
Yeah, so the other technique is called laser-induced fluorescence, which looks like it produces the fluorescence from the transitional metal lines like iron, manganese, and also the rare earths. And also very short lifetime, they're very much interested in looking at the life on Mars, bacteria or
I mean,
past
whether
life.
it's possible, whether it exists.
Yeah, existed in the past or it possible.
Oh, this is fascinating.
And then they
We
give,
should all live to 2020 so we can find out, yeah?
sure, yeah. It
Let's
will-
look at pictures. We're gonna have a picture show now, and you can tell us what these pictures are. What's that?
Yeah, so this really explains the phenomena in terms of the energy levels. So the IR, which I mentioned before, is the frequency where the molecules vibrate. So you can go from ground state, S0, to the excited state, and then you get a infrared absorption. And then if you have a light scattering from the material, you get no change in the frequency. Is called Rayleigh scattering. It's responsible for blue color of the sky and the ocean, because the short wavelength are scattered much more strongly than the longer wavelength. So what in 1928 Sir C.V. Raman found is that beside the Rayleigh scattering, there is a very weak scattering in which the frequency changes, the wavelength of the light changes. And so what happens is it goes to a virtual level and it drops down to a first excited state. And so the difference, delta nu, is the Raman shift, and that is the vibrational frequency.
And then you can read that.
Yeah, and then the other thing is that if the laser frequency is short, you can go to the electronic energy level, and then the emission is called fluorescence. It was discovered.
Fluorescence.
Yeah, fluorescence. So and then the fluorescence lifetime depend on the type of energy level it is. So from that you can also find out what kind of you can do at very trace level, a small amount of material. The biological fluorescence has a lifetime of the order of 10 picosecond. That's 10 to the power minus 11 second. So you can find out if it's biological or non-biological. And then you can also now you're measuring in the time domain. So although the frequency may be the same, but they have different lifetime. So you can identify different.
All these things help you identify.
yeah.
You know, when I go to sleep at night, Shiv, and I lay my head down on the pillow, I think about ThinkTech.
Oh, is that right?
I think about this.
Yeah.
I think about these shows and people like you. When you go to sleep at night, lay your head down on the pillow, do you think about this?
Sometimes.
What you're talking about here?
Sometimes.
Do you get ideas at 3 o'clock in the morning?
Yeah, sometimes you do.
Yeah, okay.
When I was doing my PhD and thing was hard, and then I was thinking about it, and then one morning I got up and I got it.
See,
Yeah, yeah.
It builds up in your head. Okay, what's the next picture? Let's see another picture. What is this now?
This is the telescopic Raman system. It shows the telescope on the right-hand side, and there's a small spectrograph, and then the laser, and it's coupled through the optical fiber. So this one we did it up to 66 meters in the HIG building, and we looked at it, minerals, and we detected. So this was the start of in 1989. And so from that one, we developed another system which has a much smaller fingerprint. The spectrograph is on the left, so we made a much smaller system. And so that it may be in the next figure, I think.
Okay. Well, why don't you go to the next one and see if that will help expand on this one? Is that it?
Yeah,
Okay, good.
it's called Planetary Raman spectrometer. And so it's miniaturized, and you see it's a miniaturized I60D camera, very small one. And then this is the whole spectrometer. And then we use a camera lens. And so from this one, we can detect things up to 50 meters, minerals.
So the idea is you want to advance to a further distance.
Yeah.
You want to be able to read it at a further distance.
Yeah, so the other projects are more Earth-like, trying to find these hazardous chemicals. It's funded by the Office of Naval Research. And in that one, you use a bigger telescope, we connect more light. And in that one, we can detect up to 120 meters. And my colleague has recently developed, tried the same system. It's an 8-inch telescope, and he could see as far as 1 kilometer distance.
Now, when you say see, you mean
See the
with-
spectrum.
See the
Yeah.
spectroscope.
Yeah.
And that means you see everything. You
Yes.
see any possibility
Yeah.
at 120 meters.
Yeah, yeah. And this is actually the initial telescope. It's kind of a microscope. It's kind of interesting because I was the first one. He used a pulse laser. These pulses are like 10 nanosecond wide to measure the spectrum under a high temperature. So like, the lava temperature, 1200 AVC and things like that. So this is the bottom part of it. And generally people use with the CW laser. This like continuous wave. And so it shows both of them. And those spectrometers were big. I used a whole optical table to mount the lasers and all that. But now the laser has been miniaturized. And so things have become much, much compact.
But this is a schematic of an
Sure.
actual working machine.
Oh, yeah.
Where you're just showing us how it works.
Yeah,
that's all.
sure, yeah. So we still have this system which still works.
Yeah.
It was like 1982. We set it up, yeah.
Amazing. There was a moment in my college career where I could go this way for the arts and that way for science. And I went to the arts, but I think I regret that now. I should have gone to science. You hear that, you guys? Go to science.
No, but
You
I
can
think
study the things.
it also helped in art. So in the old art,
Yeah,
they used to use minerals
yeah.
and then the glue to put it. So you can analyze the individual minerals and find out
If
for
it's a
restoring the
fraud.
old, restoring
It's a
fraud,
forgery.
a forgery, or restoring the old paintings. So they can do it. It is a whole field of art and archaeology.
But we're the real thing. We're ThinkTech. And Shiv Sharma and his research, that's the real thing. And we're going to take 1 minute break. We'll be right back. You'll see and we're gonna talk more about his projects right here in Hawaii. We'll be back.
Aloha, I'm Kili'i Akina, president of the Grassroot Institute and host on Ehana Kako, a weekly program on the ThinkTech Hawaii broadcast network. Ehana Kako means let's work together. Think of the sad alternative, let's not work together. Here in Hawaii, with all of our diversity and the richness of the people, it's important for us to come together around issues on the basis of what's right and what's good and what's going to serve the common good. And that's what we try to do at Ehana Kako. Every week, we interview movers and shakers, people in government, business, and other sectors of society to talk about how to create together a better government, economy, a better world here in Hawaii that can bless the rest of the world. I thank you for your attention to ThinkTech Hawaii, and we look forward to seeing you every Monday, 2 to 3 p.m. on the ThinkTech Hawaii Broadcast Network. We're Ehana Kako, and we wish you well. Aloha.
Okay, we're back. You know, this is all just like CSI Hawaii is what it is. CSI Manoa. We should change the name of the show. So one of the things about this thing with identifying forgeries and identifying molecules, it does lead to CSI kinds of examinations. And during the break, Shiv and I were talking about identifying people. Like in the old days, I don't know when they started doing fingerprints, it was less than 100 years ago.
Mm-hmm.
You know, you could look at the fingerprints and have a unique signature of everybody, okay? And then we looked at DNA, but now we can look at molecules and we can get an individual unique signature of anyone on the signature that the molecules in, for example, his skin is giving out, yeah?
Yeah, sure. I think you can also look at the explosives and find out what kind of explosive is there, and if it's something, like if somebody has just faked something, put some powder and all that, you can identify that. And if it's biological agents or just, regular powder, and you can do it from a distance of 100 meters or longer. So, yeah.
So you could do some real crime solving with this.
Yeah, also can help in detecting these IEDs, which
Yes.
is a nuisance.
Oh, you just focus.
Yeah.
You have that telescope
Yeah.
device,
Yeah.
and anywhere within 120 meters,
Yeah.
you'd be able to tell if it's an IUD or not.
Yeah. So
That would save lives.
Yeah. Yeah. Sure. So it has many applications.
Yeah.
Yeah.
But I asked you during the break. I said, well, you're doing molecules on the skin, or any molecule, I suppose, in the body. But why don't you just use DNA? And then you told me that, no, we can use this technology to look at DNA. Tell me how that works.
Yeah, there's a technique called surface enhanced Raman scattering. What they discovered is that if you use gold or silver nanoparticles, it enhances the Raman signal by a millionfold. And so there's a technique that people use it for analyzing very small quantities of the biological materials. It's a whole new field. And so that you can really identify what kind of molecules are there. And they are looking inside the research inside the brain, so neurotransmitters. So they can inject these nanoparticles, and then they can look at the signal, because signal is so strong, and you can look through the bone, and you can find out what's
It's
going on.
non-invasive then.
No, it's non-invasive, yeah.
You're just looking at with your spectroscopy,
Yeah,
your Raman spectroscopy,
Yeah.
and with the gold,
yeah,
the particles of gold.
and it enhances the signal.
Why gold? Why does gold do that?
There are these gold and silver. They have the other metals also have it, but they show the strongest change in the intensities. And this is called plasmon frequencies, and they get coupled with the molecules, and then they enhances the signal significantly. So for example, if you can do, you change the frequency, the Raman shift remains fixed. So if you go from near infrared, which penetrate deep inside the tissues, then you can go to visible, and then you can go to UV, ultraviolet. And ultraviolet, the most of the biological molecules, amino acids, and they absorb, and the signal gets enhanced by 1,000 times. And so you can really detect what kind of things are there. So there's a whole group at University of Pittsburgh. They are doing UV Raman, and there's a professor at University of Northwestern University. His name is Ben Dine. He developed this search technique, and so it's all called spectroscopy, but they have different application and different aspect of it.
Applications is the magic word, I think. You know,
Yeah.
Once you know you can identify things,
Yeah.
and that you have 1,000 times more visibility or 1,000,000 times more visibility, the only question is, what do you want to look at?
Yeah.
You got to figure out what you want to look at.
Yeah, sure. So at HIGP, there's a emphasis on the earth sciences and the planetary sciences. So we have our tools which can do these things. And once in a while, we adventure in different fields like biomedical.
Well,
Yeah.
yeah, let's talk about the Big Island, though. You're
Yeah.
looking at vapor on the Big Island. What are you doing there?
Yeah, so you can do, as I mentioned about this Rayleigh scattering, and there was scientists in Germany, he found out if the size of the particles is of the order of wavelength, then you get a very strong forward scattering. It's called Mie scattering. So you can look at you can analyze the gases like hydrogen, oxygen, CO2 in the air, but these particles scatter at the same wavelength. So you can map out the field of these particles, aerosol, and so on volcano you get sulfur dioxide emitting, and then it get converted into sulfuric acid, and then into the aerosol, which is like ammonium sulfate.
Which
And-
is
yeah.
sulfuric acid
Yeah,
in an aerosol. And
Yeah.
then you breathe that in, and it's going to damage your
lungs.
The
Yeah,
lungs, yeah.
yeah. So you can do with and it's called LiDAR, light detection and ranging, similar to radar.
Yeah, and that's what they were using at Oceanet, LiDAR, in order to identify particles in the wind.
Yeah, sure.
So they could see where the wind was coming from, what the patterns were in.
Yeah, yeah. So you can do the wind speed measurement or the aerosol field. And so we had this system at Bellows Air Force Base. So there are, when the wave breaks, they generate aerosol. It's called marine aerosol. And it can be so thick sometimes that you cannot see a ship. And so the ONR was interested in finding out. So we ran the project for about 3-4 years and measuring the breaking waves and aerosols. So that was fun part of it.
Yeah.
Yeah.
It's like a secret weapon, except it's not secret. Doing amazing things. But you know, now you've been doing this for, my calculation could be 35 years.
Yes, sure.
35 years. And it's been expanding. It's been going great distances,
Yeah.
much more accuracy,
Mhm.
more applications, smaller distances. I mean, the whole world around us is your oyster, actually. But where is it going to go from here? I mean, there must be things in your vision of this
Yeah.
kind of technology, this combination of technology.
Yeah.
Where is it going to go? What do you see doing in the years to come?
Yeah, so I think interesting part is in HIGP, we have people who have different interests. So I have a colleague, Paul Lucy. He came to me one day and he said, Shiv, can you make a mineral at a distance? And I said, I don't have a telescope and I have never done that. So he said, oh, I have a telescope. So he brought a small telescope. And that was the start of this planetary explanation. And we just set it up crudely and we could see things at 10 meters in the lab. And so from there we start developing. So people come with different ideas and then you will kind of say, okay, let's try to do it. And of course you develop the technique. As I mentioned for the biomedical field, Lori Kawimoto, it looks very simple, but most of the people in medical sciences, they use glass slides. And the glass slide is thick, few millimeter, and you put a cell which is like 10-20 microns in size. And so when we looked at it, we saw only the glass rather than looking at the cells. And so then we came up with this, we have Anupam Mishra, he's a colleague. He came up with the idea that maybe we should coat the slides with a reflecting coating, and that worked very well. So, and then we got idea, okay, so if you put a liquid on a slide, it spreads out, so you get a very thin film. So we came with the idea, so let's make a micro cavity. So basically you take a sphere of 100 micron or 10 micron and put between the two aluminum slides, and then you press them and you take it out, then you get a hemispherical cell. And that worked very well. So we could use those, or we can coat it with gold and silver, and then enhance the signal
Enhance the
that way.
signal, yeah.
So it's just really when you come up with the application, you try to work on it, and then it works very well. So in different areas, different fields, and it's expanding. And you can use optical fiber at a distance. And so we are thinking about it on the Big Island. They took this LiDAR system, and so they have to go away like 1.2 kilometer. But there's the other problem. There are nest of the birds in the crater, and so they were worried about the birds. And so we came up with the idea, maybe we should use an optical fiber so that the light will not be seen by anybody and just measure at the source. So our director is very much interested in it, and so we are working on that. So it's just
So it's interesting, you can try one of your technologies,
Yeah.
and if there are hitches with that, then to do the same work, bring in the other technology.
yeah, sure, yeah,
And
yeah.
make combinations of these technologies.
Yeah.
What's your favorite one? What's the one that, you really have, you see promising?
Right now, the one is working on Mars. That's the
Yeah,
favorite one.
okay.
And we also developing an instrument which can detect things underwater, which is being developed in the lab right now. And so the story goes like, well, okay, if you have somebody in the harbor put some things like ammonium nitrate and put a
Like
fuse
explosive,
on it,
yeah.
explosives, and then you can blow up the boats or the ships.
Yeah,
And so we developing this thing underwater. And so you can do it. You have to put all the equipment inside a pressure housing and have a window. And so we are working on that. So that will be an interesting
you
application.
can spot the ammonium nitrate underwater.
Oh, any chemicals.
Yeah. This is amazing stuff. You haven't heard of this. And ThinkTech wants to cover it more.
Oh,
Shiv.
sure.
We want to follow you. We want to walk down that trail with you and see all these fabulous things happening. It is so exciting. It makes CIS look like a piker, yeah. That's Shiv Sharma, fabulous researcher at UH in Manoa, Associate Director of the Hawaii Institute of Geophysics and Planetology in the School of Ocean and Earth Science and Technology. We really enjoy having you here, Shiv. Thank you so much.
Thank you so much.
Aloha.
Aloha.